Bismillah ar-Rahman ar-Rahim. We are going to talk about osmolality. Osmolality, when we talk about osmolality, we have to take care that we are talking about the number of particles. We are not talking about the charges, the number of particles in a solution. So osmoles means 1 mole solid particle. When we say, look at it. If we are talking about sodium chloride dissociates completely into sodium and chloride. So the number of particles will 2 particles. Look at glucose. Glucose is 1 particle. So when we talk about glucose, it is 1 particle. When we talk about sodium chloride, it's 2 particles. So we count and calculate the number of particles in solution. So this is the osmolality or osmolarity. The osmolarity is the number of particles or osmoles per kilogram. Kilogram water. Osmolarity, this is osmoles per liter. But the problem here, when we talk about osmolarity per liter or osmolality per kilogram, 1 liter of plasma would be equivalent to 1 kilogram of plasma, because the water, 1 gram of water, 1 ml of water equals 1 gram, and so 1 liter equals 1 kilogram. So there is no difference between osmolarity and osmolality, because the solvent itself, 1 liter equals 1 gram, 1 kilogram. When we count the osmolarity, or when we calculate it, so we usually multiply 2 by sodium, because sodium is 1 molecule and is attached to another molecule like it. So we multiply it by 2. And when we come to glucose, in the normal person, if the concentration is 100 milligram percent, this means that its concentration is 1000 milligram per liter. When we divide it by the molecular weight of glucose, which is 180 kilodalton, this means that you will convert it from milligram into mil equivalent. The same for blood urea nitrogen, which will be multiplied per liter by the molecular weight, which is 28. The total osmolarity or osmolality of the plasma will be 285 millismoles. The osmolarity, the total osmolarity, since the ions do not behave entirely independently in solutions because of inter-ionic attractions between them, one can correct for this deviation by using the osmotic coefficient factor, which is equal to 0.93. We discussed this problem, this slide before, when we measure the total osmolality or osmolarity of the plasma. We will count the sodium, the potassium, the calcium, the magnesium, the chloride, bicarbonate, all of them. But these, all of them, they are in mil equivalent or millismoles. When it comes to, we will see how to convert the albumin or the protein to millismoles. For sure, this will be divided by its molecular weight. And we came to the conclusion that when we calculate them, the total osmolality would be 301 for the plasma, 300 for the interstitial tissues. And the difference between the two, as I have mentioned before, is the 1 ml equivalent of protein and excess of that of interstitial, which is 0.2. But the corrected osmolarity, when you multiply it by 0.93, This will give you the corrected osmolality, which is 282 for the plasma and 281 for the interstitial tissues. And this is the osmolality. When you convert it to osmotic pressure, you multiply it by 19, and in this case the total osmotic pressure for the plasma will be 5443 millimeter mercury, compared to the interstitial, which is less by 20, and it is 5423 millimeter mercury. So the osmotic pressure, the sucking pressure of the plasma is more than that of the interstitial tissues by 20 millimeter mercury, due to the difference in plasma protein, which is more than that of the interstitial fluid. So this is very important to be considered while you are talking about the osmolarity. This is very simple. How can we measure or calculate the osmolality? If you look at the sodium, this is the sodium. Sodium is made in the form of sodium chloride. Sodium chloride, 106 milliequivalent of sodium, 106 milliequivalent of chloride. Sodium bicarbonate, 24 milliequivalent, 24 milliequivalent. Sodium other salts. So when we measure sodium from one point, you can multiply it to give you the other partner of it. So these are the number of particles, number of particles of sodium attached to another molecule with a chloride, bicarbonate, and so forth. When you come to the same thing for the potassium, when you come to glucose, as I mentioned, the normal level of glucose is, say, if it is 100 milligram percent, it is 1000 milligram percent, and the molecular weight is 180. So the value of glucose will be about 5 milliequivalent per liter. When you come to the protein, the albumin itself, the normal level of albumin is about 4 gram or 4.5 gram percent, or 45 gram per liter, and the molecular weight of albumin is 68 kilodalton. So the total amount of albumin will be about 0.6 milliequivalent per liter. When you come to the globulin, which is about 3.5 gram percent or 35 gram per liter, and the mean, we have different types of globulins, alpha, beta, gamma globulins, and the mean molecular weight is about 100. So this means that it, it has a value of 0.35 milliequivalent. So the total about 1 plus milliequivalent. So this is a protein. The same thing for bradyurea nitrogen. So if it is about 10, if it is about 10 milligram percent, it is equal to 100 milligram per liter, and the molecular weight is 28, so it has a value of about 3 or 3.5 milliequivalent. So this is the calculations of it. When you sum them up, it's about 300, and you multiply by the coefficient factors. In this case, you will get the normal value. We have mentioned before that those plasma osmotic pressures is about 4,000, 5,440, and that of the interstitial fluid, extracellular fluid, is about 5,420. The difference is 20 millimeter mercury. This is oncotic pressure due to the increase in the protein of the plasma is more than that of the interstitial tissues by about 1 milliequivalent. So osmolarity is defined as concentration of solutes per liter of solution. And thank you very much.